Welcome to EE16B Video Notes for Intro to Transistors and Digital Logic. My name is Safin Patel, and let's get started. So in this class, we will talk about both digital and analog circuits. We're going to start off here, and we're going to start talking about digital. This whole lecture and the next series is going to all be about digital circuits. So what is a digital circuit, fundamentally? Well, a digital circuit, we could define it as a type of circuit that takes as its input logical zeros and ones, put it into a circuit, and as its output, we also have logical zeros and ones. So, on the surface, this seems like a waste. If you have an analog circuit, you can have a continuum of values for your input and your output. So, why on earth would you say, oh, I only want zeros and ones? Well, the question's the answer is a little bit subtle. So, why digital? The big reason is what we call noise. So, let's say, for example, on your input side of your circuit, suddenly a cosmic ray appears, and instead of a 0, you get a 0.2 as your input. What do we want our output to be? Well, we want our output to still be a 0 or a 1. And that's what digital circuits allows us to do. We have what we call a noise margin. Our input can vary depending on the type of circuit we're using, from say 0.0 to 0.2 or 0.8 to 1 for the one side, and we still get as our output clean zeros and ones. So immunity to noise is really, really important, and it allows us to make easy circuits, and basically our computers still function. It could mean that a cosmic ray comes from the sun and hits our circuit and starts changing things. It could be that instead of operating our circuit in California, we operate it in Siberia with much lower temperatures and much different humidity conditions. But the point is that the digital circuit is very immune to all different types of noise, and that's really important. Another reason is that because of this noise immunity, it means that we have simpler and smaller circuits. And again, this is really, really important because it means that we can have tiny computers and they're easy to design. We can design large logic blocks thinking that, oh, we know that our inputs are always zeros and ones and our outputs are always zeros and ones, so we don't really necessarily have to worry about what happens in the middle. So this is something to think about when we design digital circuits. We always want our inputs and our outputs to both be zeros and ones. We don't want them to be things in between. Okay, so how do we design a digital circuit? Well, we design them with transistors. So the question is, what is a transistor? A transistor is an electrically driven switch. So what that means is instead of a mechanically driven switch like you would have, in a regular circuit board, we have an electrically driven one. So instead of flipping it, we apply a voltage to the gate terminal and the switch turns on or off. So there's a lot of different types of transistors, and in this class we will be talking specifically about MOSFETs. What is a MOSFET? A MOSFET is a metal oxide semiconductor field effect transistor. So this is a lot of words, and it's a little bit to digest, but we don't really need to worry about what it means. This is just so that you understand if you see different circuit symbols in other textbooks, or if you Google transistors, that you see other things. This is what we're talking about. There's BJTs, HEMTs, but they're not of interest in this course. So there are two main types of MOSFETs. We have PMOSs and NMOSs, and we draw them like this. Okay, so they're both three-terminal devices. They both have a gate, source, and drain, like so. The difference is the PMOS has the source on top and the drain on bottom. This is by convention. You might actually see it drawn in different ways in different places. So what is the model that we use for the circuit? Well, as I said, it's electrically driven. So what we like to change is VGS. This is the gate to source voltage. So when the gate to source voltage goes above some threshold, let's call it VTN for the NMOS, and VTP for the PMOS, then this is what we call the on stage. So it turns into the following. We have a gate, and then we have a capacitor to ground, and then we have a resistor between the drain and the source, and we call this R on. And we have some current IDS. Similarly with the PMOS, again we have a capacitor to ground, we have an R on, and we have current going from source to drain. Difference is in PMOS, it goes in the opposite direction, it goes from source to drain instead of drain to source. Okay, now how about the off stage? What happens when VGS is greater than VTN? And in the PMOS stage, what happens when VGS is greater than VTP? Oops, this should be less than. In this case, then we have off. We still have the capacitor to ground, but instead we have an open circuit. And no current flows. They are electrically disconnected, the drain and source. Again, electrically disconnected. So what are common values for this threshold voltage? Well, on the NMOS side, for VTN, generally, for most transistors that you can buy off the shelf, you have about 0.2 to 0.7 volts for your VTN. And then for the PMOS, VTP is about negative 0.2 to negative 0.7 volts. So now that we've talked about transistors, how do we make a useful circuit out of it? So let's talk about the most basic circuit that we can think of. Let's just take an NMOS transistor, connect the source to ground, and then we're going to control the gate with Vin. And for the output, we're going to take a resistor and VDD. So we're connecting the drain to a resistor to VDD, and this is sort of a poor man's inverter, and we'll talk about what that means. So we've been talking about the digital abstraction, right? So with the digital abstraction, we only care about zeros and ones. That means that Vin is equal to 0 or VDD, and Vout, ideally, should be equal to 0 and VDD as well. We don't want intermediate values because that breaks our digital abstraction and could, break things further down our circuit line if we take Vout and put it into a different circuit as an input. Okay, so Vin and Vout. So the two values that we care about, 0 and VDD. What does the Vout value become? Okay, so Vin equals VDD. Vin equals 0. That means that VGS equals 0 as well, and therefore then the transistor is in the off stage. Oops. So we have it in the off stage. What happens? Let's draw the circuit. So we have capacitor to ground from the gate. We have a resistor. This is connected to VDD. This is Vout. R. And perfect. So what we have here is the VDD is connected by a resistor to Vout, and then it's not connected at all to ground. So that means that Vout should be equal to VDD. Okay, how about the case where Vin equals VDD? VGS is equal to VDD, which is above the threshold voltage. We're going to assume that. And we have the following. We have our R on bottom, and R on top. This is V out. So the top is connected to VDD, and the bottom is connected to ground. So V out is connected by a voltage divider to the source. So V out is equal to VDD R on over R plus R on. And let's call this VDiv. So this, it works as an inverter, right? As long as we choose VDiv to be, some value that's very, very small, so that, so as long as VDiv, we want VDiv to be approximately equal to 0. And for that to happen, then we want R to be much greater than R on, or R on to be very small. So this is one way of designing an inverter, and this has a few problems. The first is power consumption. So let's talk about problems. So power consumption. No matter what, you have some connection from the rail, VDD, to ground. And especially with this voltage divider, then there will always be a large power consumption, and that's a problem. We generally want, when we design these types of circuits, we want them to be low power consumption, just so our chips don't fry and we don't have to have a large battery. So that's one problem. And the second one is that it's breaking our digital abstraction. If you notice, VDiv is not precisely equal to 0, and unless R is much greater than R on, then we can't guarantee that VDiv is close to 0. And that's a problem. So how do we fix these? Well, instead of a resistor, we can put a different type of transistor. So enter the CMOS inverter. So let's draw this circuit. What does a CMOS inverter look like? So we have two transistors. We have a PMOS and an NMOS. Their gates are connected here. Source is at the top, and both of them have their drain here. Connected to the V out. Source terminal of the NMOS is grounded, and the source terminal of the PMOS is connected to the rail. So this is V in. Let me draw that better. V in, and goes to these two transistors, and then we have V out. So let's analyze this. Because we're talking about digital again, we care about two values for V in, and we want them to translate precisely to two values of V out. So we have 0 and VDD. So let's analyze the circuit. So if V in equals 0, that means VGS and MOS equals 0, and VGS for the PMOS equals negative VDD. So in this case, what does the current circuit look like? For VGS equal to 0 for the NMOS, that means that this is off. And then the PMOS for negative VDD, that means it's approximately on. So we're making assumptions that, VDD is greater than the threshold voltages, but for a well-designed circuit, this is almost always true. Okay, so let's draw this circuit out. So if the NMOS is off and the PMOS is on, that means for V in, we have two capacitors to ground, one each from each of the transistors, and we'll talk about the significance of these two capacitors later, why they're important in our circuit modeling. Okay, and then, so that's on the input side. These are the two gates. And then on the output side, the NMOS should be off, so it looks like this. And then this should be connected to VDD. This is R on, and this is V out. So as we can see, VDD is connected by a small resistor to V out, and The only thing separating them is R on. So this should be approximately VDD. Okay. So how about Vin equal to VDD? In this case, VGS equals VDD for the NMOS, and VGS equals 0 for the PMOS. So we have the PMOS being off and the NMOS being on. So what does that look like? That means that we again have the two capacitors for Vin for the input side, and for the output side we have no electrical connection between VDD and Vout, but a resistor between Vout and ground. So this basically makes a good connection between Vout and ground, and we have Vout being 0. So we've effectively fixed the two problems that we had before. If you notice, in both scenarios, there's no electrical connection, a perfect electrical connection between VDD and ground. That means in static, there is, what I mean in static is that when we're not switching, when we're not, going from Vn equal to 0 to VDD, as we're not trying to change the value, no static power consumption. And this is really important. That means that if we just leave our computer on, generally not doing anything, then power consumption is usually very low. So that means that, our batteries last longer and our computers don't start burning up. Great, so no static power consumption, and the digital abstraction holds. So these are both very good, and this makes for a very good simple circuit for digital applications. So what do we do? We just made a circuit that says Vout equals not Vin. And this is the simplest digital circuit we can make. And we'll continue talking about how we can design larger, more complicated digital circuits for this. Okay, one last thing. So I talked before about noise margins. So how do we analyze the noise of the circuit? And how do we analyze what a good digital circuit looks like? So what we do is we look at something called the voltage transfer curve, or VTC. Voltage transfer curve. Or voltage transfer characteristics. So we'll make a graph. On the y-axis is Vout. On the x-axis is Vin. Okay. So we're going to divide this into 3 sections. The first one is from Vn equal to 0 to Vtn. In this region, we know that the NMOS is off and the PMOS is on. So, let's draw the graph in blue. So that means that this is where Vout is equal to VDD. Okay. And then similarly, on the higher side, when we have VDD minus VTP, this is VDD. So at this point, Vout is equal to 0 for Vin between VDD and VDD to minus VTP. To VDD minus VTP. Okay, so what happens, this is the region where the NMOS is on and the PMOS is off. Okay, so what happens in this middle region where the NMOS is on and the PMOS is on? Let's analyze this really quick. So with our current model, if VGS is between if when Vin is between VDD minus VTP and VTN. That means that the NMOS is on and the PMOS is on. We can see this because when we draw the circuit, so in this range, because Vin, so the VGS for the NMOS is greater than VTN, as we can see here. So this is GS, and then NMOS, and then the VGS for the PMOS is less than VTP. And obviously these are both on in this case. So let's draw this circuit. Again, we have the two input capacitors, and then we have two resistors. All right. So let's call this R on P, and this is R on N. So in this case, V out is equal to VDD R on N over R on N plus R on N plus R on P. So in general, when we design these, R on N we can say is about equal to R on P, and therefore V out is approximately equal to VDD over 2. So that puts it, blue, that puts it somewhere here. So this is approximately equal to VDD over 2. So if you noticed, we talked about the digital abstraction, right? Well, where does the digital abstraction break? It breaks in this middle period. So in general, we try to avoid this middle period, this middle region. And how do we do that? Well, we make sure that our input is between 0 and VTN, or VDD minus VTP and VDD. We want to keep it in these regions. And this is what we call our noise margins. So if our input is somewhat noisy, if a cosmic ray comes from somewhere, and instead of precisely 0, we're at, a half VTN, then we are still guaranteed that our output is at VDD, which is really important for designing these circuits. We know that there's a large immunity to noise, and we don't really need to worry about random cosmic rays coming out of nowhere, or temperature variations, or things like that. In the next video lecture, we'll talk more about CMOS logic and how we build larger circuits out of using these concepts.